Imagine a black hole devouring a star, its gravity tearing the celestial object apart in a cosmic feast of plasma and light. But then, something extraordinary happens. For weeks, astronomers witnessed this hungry monster expelling a torrent of superheated gas, creating a glowing donut-shaped structure around it, brighter than any star in the universe. The black hole, which had been feasting on a star 10 times the mass of our Sun, suddenly rejects its meal, hurling material outward in a violent, uncontrolled eructation. The event, captured in infrared light, reveals a chaotic dance of debris and radiation, a cosmic belt so powerful it briefly outshines entire galaxies. What began as a feeding frenzy ends not with satiation, but with a catastrophic overflow, as if the black hole's insatiable appetite has finally met its limits. This isn't just a spectacle, it's a rare glimpse into the turbulent life of these cosmic beasts, where even the universe's most powerful engines can suffer indigestion. In a groundbreaking observation, astronomers have captured the dramatic final moments of a black hole's feeding frenzy, witnessing what scientists are calling a bad case of cosmic indigestion. This event, which unfolded in a distant galaxy 270 million light-years away, offers a rare glimpse into the chaotic dance between a supermassive black hole and the star it devours. The discovery, made possible by advanced telescopes and multi-wavelength observations, reveals how these cosmic monsters not only consume their prey but also eject vast amounts of energy in a final, explosive outburst. This chapter explores what exactly happened, how scientists tracked the event, and why such observations are crucial for understanding the universe's most extreme environments. At the heart of this discovery is a supermassive black hole, millions of times more massive than our Sun, lurking at the center of a distant galaxy. For years, astronomers have known that such black holes can occasionally feast on nearby stars, a process known as a tidal disruption event. When a star ventures too close to a black hole, the immense gravitational forces tear it apart, creating a luminous explosion of gas and debris. However, what makes this particular event unique is the way it unfolded. Rather than a steady, prolonged feeding, the black hole's consumption of the star was followed by a dramatic release of energy, akin to a creature vomiting after overeating. The process began when a star, likely a sun-like object, strayed too close to the black hole. As it approached, the black hole's gravity stretched the star into a long, glowing strand, a phenomenon known as spaghettification. The star's material was then pulled into an accretion disk, a swirling ring of gas and dust that heats up to unimaginable temperatures as it spirals toward the event horizon, the point of no return. This disk emits intense radiation, primarily in the form of X-rays and ultraviolet light, which astronomers can detect even from such vast distances. However, the true drama unfolded not in the act of consumption but in the aftermath. As the black hole continued to devour the star, the accretion disk became unstable, leading to a sudden surge in energy output. This surge, detected by telescopes like the Event Horizon Telescope and the Very Large Array, was not a steady glow but a violent, explosive release of energy. The black hole, in a sense, vomited the excess material into space, creating a powerful jet of particles traveling at near-light speeds. This jet, observed in radio waves, was the final act of the black hole's feeding frenzy, a cosmic equivalent of a creature expelling undigested food after a binge. The significance of this observation lies in its implications for understanding how black holes interact with their surroundings. While tidal disruption events are relatively rare, they provide critical insights into the behavior of supermassive black holes, which are thought to reside at the centers of most galaxies. These events also shed light on the role black holes play in shaping their host galaxies, as the energy released during such outbursts can influence star formation and the distribution of matter in the galaxy's core. The recent observation, however, adds a new layer to this understanding by demonstrating that black holes can eject vast amounts of energy in a single, explosive burst rather than over an extended period. To capture this event, astronomers relied on a combination of advanced telescopes and observational techniques. The Event Horizon Telescope, which famously imaged the black hole at the center of our Milky Way, played a key role in detecting the radio emissions from the jet. Meanwhile, other observatories, including the James Webb Space Telescope and the Chandra X-ray Observatory, provided crucial data on the high-energy emissions from the accretion disk. By combining observations across different wavelengths, radio, X-ray, and optical, scientists were able to piece together the full story of the black hole's feeding frenzy and its aftermath. One of the most intriguing aspects of this event is the timing of the outburst. Unlike previous tidal disruption events, which typically emit energy over weeks or months, this particular outburst was exceptionally short-lived, lasting only a few days. This rapid release of energy suggests that the black hole's accretion disk underwent a sudden instability, possibly triggered by the uneven distribution of material or the presence of magnetic fields. Such instabilities are not fully understood, making this observation a valuable case study for astrophysicists seeking to model the complex dynamics of black hole accretion. The study of tidal disruption events also has broader implications for our understanding of the universe. These events are thought to be one of the few ways astronomers can directly observe the effects of a black hole's gravity on a star, providing a unique opportunity to test theories of general relativity in black hole physics. Moreover, the energy released during these outbursts can have far-reaching effects on the surrounding environment, potentially influencing the evolution of galaxies and the distribution of cosmic material. By studying these events, scientists hope to uncover more about the life cycles of black holes and their role in the cosmic web. Despite the dramatic nature of this observation, it is important to note that such events are not entirely unpredictable. Theoretical models suggest that tidal disruption events occur when a star passes too close to a black hole, often due to gravitational interactions within the galaxy. However, the exact frequency and characteristics of these events remain subjects of ongoing research. The recent observation, with its unique combination of a short-lived outburst and powerful jet, challenges existing models and highlights the need for further study. The discovery also underscores the importance of long-term observational campaigns in astronomy. Many of the tools used to study this event, such as the Event Horizon Telescope and the James Webb Space Telescope, are the result of decades of technological advancement and international collaboration. These instruments allow astronomers to peer into the distant universe with unprecedented clarity, enabling them to witness phenomena that were once thought to be beyond our reach. The ability to capture such a dramatic event as a black hole's feeding frenzy and its aftermath is a testament to the power of modern observational astronomy. In conclusion, the observation of this black hole's feeding frenzy and subsequent cosmic indigestion represents a milestone in our understanding of these enigmatic objects. By studying the intricate processes that govern their behavior, scientists are not only unraveling the mysteries of black holes but also gaining insights into the fundamental forces that shape the universe. As technology continues to advance, future observations may reveal even more about the dynamic and often violent interactions that occur in the hearts of galaxies, further expanding our knowledge of the cosmos. For decades, astronomers have studied black holes as cosmic vacuum cleaners, pulling in gas, stars, and even light with their immense gravity. But what happens when a black hole's meal comes to an end? Recent observations have revealed a startling phenomenon. When these hungry giants stop feeding, they don't simply go quiet. Instead, they erupt in a dramatic outburst, a kind of cosmic indigestion that sends shockwaves through space. How did scientists catch this moment? It required a combination of cutting-edge technology, decades of preparation, and a global network of observatories working in perfect harmony. Let's walk through the process that led to this extraordinary discovery. The story begins with a black hole at the heart of a distant galaxy, one of the millions scattered across the universe. These cosmic monsters are typically surrounded by a swirling disk of gas and dust, known as an accretion disk, which heats up to unimaginable temperatures as it spirals inward. The energy released is so intense that it outshines entire galaxies. But this feeding frenzy doesn't last forever. When the supply of material dwindles, the black hole's behavior changes. The question was, how do astronomers detect this transition? And more importantly, how do they capture the aftermath of a black hole's final meal? The answer lies in a combination of telescopes and instruments designed to observe the universe across different wavelengths of light. One of the most critical tools was the Event Horizon Telescope, or EHT, a network of radio telescopes linked together to create a virtual telescope the size of Earth. The EHT has already produced groundbreaking images of black holes, including the first-ever image of the supermassive black hole at the center of our galaxy, Sagittarius A star. But in this case, the team focused on a different target, a black hole in a distant galaxy known as NGC 1365. This galaxy is a prime candidate for studying black hole activity because its central black hole is actively accreting material, making it an ideal laboratory for observing the feeding process. However, the EHT alone couldn't provide the full picture. To understand the black hole's behavior, scientists needed to combine data from multiple observatories. X-ray telescopes, such as NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton, were essential. These instruments detect high-energy radiation emitted by the accretion disk as it heats up. When a black hole is actively feeding, the X-ray emissions are intense, but as the material supply dwindles, these emissions can fluctuate dramatically. By monitoring these changes, astronomers could track the black hole's transition from a voracious eater to a starved giant. The process of gathering data was meticulous. Observations required precise timing, as the black hole's activity could change on timescales ranging from minutes to years. For example, the team used the Swift Observatory, which is optimized for detecting sudden bursts of gamma rays, to monitor for any explosive events that might signal the end of the feeding frenzy. Meanwhile, radio telescopes like the Atacama Large Millimeter/Sub-Millimeter Array (LLMA) provided additional insights into the structure of the accretion disk and the jets of plasma that often accompany black hole activity. These jets, which can stretch millions of light-years across space, are powered by the black hole's spin and magnetic fields, and their behavior can offer clues about the state of the accretion disk. But the most dramatic evidence came from a phenomenon known as a tidal disruption flare. This occurs when a black hole tears apart a nearby star, creating a brilliant explosion of light as the star's debris spirals into the black hole. However, in this case, the event wasn't caused by a star being consumed, it was the result of the black hole's own feeding process coming to an end. As the supply of material in the accretion disk dwindled, the black hole's immense gravitational pull began to exert a different kind of influence. Instead of continuing to devour, it released a sudden burst of energy, a kind of cosmic belch that sent shockwaves through the surrounding space. This outburst was detected across multiple wavelengths, from radio waves to X-rays, creating a multifaceted view of the event. The timeline of the observation was as complex as the phenomenon itself. The process began years before the actual event, with astronomers setting up long-term monitoring campaigns. These campaigns involved regular observations of the black hole's activity, collecting data over extended periods to detect subtle changes. When the first signs of a decline in activity were noticed, the team intensified their efforts, coordinating observations across different telescopes to ensure they captured every possible detail. The data collection phase was a race against time, as the black hole's behavior could change rapidly, and missing a critical moment could mean losing the chance to study the event at all. Once the data was collected, the real challenge began: analysis. The raw data from the telescopes needed to be processed and interpreted. This involved sophisticated algorithms and simulations to model the behavior of the black hole and its surroundings. For example, the team used computational models to simulate how the accretion disk would behave as it transitioned from a state of high activity to one of dormancy. These models helped them understand the physical processes at play, such as the magnetic fields that channel energy into jets or the radiation emitted as material falls into the black hole. By comparing the observed data with these simulations, the team could confirm their hypotheses and refine their understanding of the event. One of the most remarkable aspects of this discovery was the collaboration between different observatories and research teams. The EHT, Chandra, XMM Newton, Swift, and ALMA were all part of a global network of instruments working in unison. This collaboration required seamless coordination, as data from different telescopes had to be synchronized and analyzed together. For instance, while the EHT provided high-resolution images of the black hole's environment, the X-ray telescopes offered insights into the high-energy processes occurring within the accretion disk. By combining these datasets, the team could build a comprehensive picture of the black hole's behavior, from its immediate surroundings to the far-reaching effects of its outburst. The significance of this discovery extends beyond the immediate observation. It provides crucial insights into the life cycle of black holes and their role in the universe. Black holes are not just cosmic vacuum cleaners, they are dynamic entities that influence their surroundings in profound ways. The outburst observed in NGC 1365 suggests that even when a black hole stops feeding, it can still release immense amounts of energy, shaping the environment around it. This has implications for our understanding of galaxy evolution, as black holes are known to regulate star formation by their energetic outflows. By studying these events, astronomers can better model how black holes interact with their host galaxies and how they contribute to the large-scale structure of the universe. The process of discovery also highlights the technological advancements that make such observations possible. The EHT's ability to image black holes with unprecedented resolution is a testament to the power of interferometry, a technique that combines signals from multiple telescopes to create a single, high-resolution image. Similarly, the X-ray telescopes used in this study rely on advanced detectors and cooling systems to capture faint signals from distant objects. These technologies, developed over decades of research and engineering, enable astronomers to peer into the most extreme environments in the universe and uncover secrets that were once beyond our reach. In the end, the observation of this black hole's cosmic indigestion was a triumph of human ingenuity and collaboration. It required not only the latest technology but also the patience and dedication of scientists working across disciplines and continents. The data collected from this event will continue to be analyzed, offering new insights into the nature of black holes and their role in the cosmos. As we look to the future, the tools and techniques developed through this research will undoubtedly lead to even more groundbreaking discoveries, deepening our understanding of the universe and its most mysterious inhabitants. Astronomers watch a black hole's feeding frenzy end with a bad case of cosmic indigestion. This part of our deep dive into astronomers watch a black hole's feeding frenzy end with a bad case of cosmic indigestion focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. Astronomers watch a black hole's feeding frenzy end with a bad case of cosmic indigestion. This part of our deep dive into astronomers watch a black hole's feeding frenzy end with a bad case of cosmic indigestion focuses on, give historical context, how our understanding of this general topic evolved over past decades, earlier missions, or discoveries that led up to this moment. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. As astronomers watched the dramatic spectacle of a black hole's feeding frenzy, they were left with more questions than answers. The event, which saw a massive outflow of material from the black hole's vicinity, was both a marvel of cosmic scale and a puzzle of profound complexity. While the observation itself was a triumph of modern astronomy, it also exposed gaps in our understanding of how black holes interact with their surroundings. The sudden cessation of the feeding frenzy, this so-called cosmic indigestion, raises fundamental questions about the physics of accretion disks, the role of magnetic fields, and the nature of the material being ejected. Scientists are still debating the exact mechanisms at play, and the event has sparked a wave of new hypotheses and experimental approaches. But what exactly remains unresolved? Let's explore the mysteries that linger in the wake of this cosmic drama. One of the most pressing questions revolves around the nature of the outflow itself. The observations revealed a massive ejection of material, but the exact composition and origin of this outflow remain unclear. Was it gas, dust, or something else entirely? Theories suggest that the material could be remnants of the accretion disk, which is a swirling disk of gas and dust that spirals into the black hole. However, the sudden expulsion of such a massive amount of material defies simple explanations. Some scientists propose that the outflow might have been triggered by a sudden change in the black hole's environment, such as a nearby supernova or a collision with another celestial object. Yet, no such event has been observed in the vicinity of the black hole, leaving the cause of the outflow a mystery. Another area of debate centers on the role of magnetic fields in the process. Black holes are known to have incredibly strong magnetic fields, which can influence the behavior of the surrounding material. Some researchers believe that these magnetic fields might have played a key role in the outflow, perhaps channeling the material into jets or creating turbulence that disrupted the accretion process. However, the exact mechanism by which magnetic fields could have caused such a dramatic ejection is still under investigation. Theories suggest that the magnetic fields might have become unstable, leading to a sudden release of energy that propelled the material outward. Yet, the precise conditions required for such an instability to occur remain uncertain, and more data is needed to confirm these hypotheses. The timescale of the event also presents a puzzle. While astronomers observe the outflow over a period of weeks or months, the exact duration of the feeding frenzy and the outflow itself is still a matter of debate. Some estimates suggest that the feeding frenzy lasted for several months, but the precise timeline is difficult to determine. The sudden cessation of the feeding frenzy, this so-called cosmic indigestion, raises questions about the dynamics of the accretion process. Was the outflow a sudden burst, or did it occur over a longer period? The answer could provide crucial insights into how black holes regulate their energy output and interact with their surroundings. However, without more detailed observations, these questions remain open. The composition of the ejected material is another area of uncertainty. While the outflow is believed to consist of gas and dust, the exact elements and their abundance are still unclear. Some scientists speculate that the material might contain heavy elements formed in the intense heat and pressure of the accretion disk. However, the presence of these elements would depend on the specific conditions in the disk, which are not yet fully understood. Additionally, the outflow might have included material from other sources, such as nearby stars or interstellar medium, but the extent of this contribution is still unknown. These questions are critical for understanding the chemical evolution of galaxies and the role of black holes in shaping their environments. Perhaps the most intriguing mystery is the broader implications of the event for our understanding of black hole physics. The observation of such a dramatic outflow challenges existing models of how black holes accrete matter and release energy. While some theories suggest that outflows are a common feature of black hole activity, the specific conditions that lead to such a massive ejection are still poorly understood. Scientists are now exploring whether this event is an isolated occurrence or part of a larger pattern. If similar outflows are observed in other black holes, it could indicate a more widespread phenomenon that requires a re-evaluation of current models. However, without more data, it's difficult to determine the significance of this particular event. The observational challenges of studying such events also highlight the limitations of current technology. While modern telescopes have allowed astronomers to observe the outflow in unprecedented detail, there are still gaps in our ability to measure certain properties of the material being ejected. For example, the exact velocity and direction of the outflow are difficult to determine with current instruments, which means that some aspects of the event remain speculative. Additionally, the vast distances involved mean that even the most advanced telescopes can only provide a limited view of the process. These limitations mean that some aspects of the event may never be fully resolved, at least with current technology. Despite these uncertainties, the observation of this event has already sparked a wave of new research and theoretical models. Scientists are now working to refine their understanding of black hole accretion and outflow mechanisms, and the event has provided a unique opportunity to test these theories. Some researchers are focusing on simulating the event using computer models to see if they can replicate the observed phenomena. Others are looking for similar events in other parts of the universe to determine if this is a rare occurrence or part of a broader trend. These efforts are crucial for advancing our knowledge of black holes and their role in the cosmos. In the end, the event serves as a reminder of how much we still have to learn about the universe. While astronomers have made tremendous strides in understanding black holes, the observation of this feeding frenzy and its aftermath has exposed the limits of our current knowledge. The questions raised by this event are not just about the mechanics of a single black hole but about the fundamental processes that govern the behavior of these enigmatic objects. As scientists continue to explore these mysteries, they are not only uncovering the secrets of black holes but also deepening our understanding of the universe itself. The journey to answer these questions is just beginning, and the next steps will undoubtedly lead to new discoveries and a more complete picture of the cosmos. As we look ahead, the next chapter in our understanding of black holes will be written by the next generation of telescopes and observatories. These instruments, designed to peer deeper into the cosmos than ever before, will not only confirm the dramatic events we've already witnessed but also challenge our assumptions about how black holes grow, consume, and interact with their surroundings. The James Webb Space Telescope, for example, is already revolutionizing our view of distant galaxies and their central black holes. With its unparalleled sensitivity to infrared light, it can peer through the dust veils that obscure these regions, revealing the intricate dance of material spiraling into a black hole's event horizon. By studying the light emitted from these accretion disks, astronomers hope to map the extreme physics at play: how gas heats up to millions of degrees, how magnetic fields channel energy, and how the black hole's gravity warps spacetime itself. But Webb's capabilities are just the beginning. Future missions like the Lynx X-ray Observatory, set to launch in the coming decades, will offer even higher resolution views of the high-energy emissions produced during a black hole's feeding frenzy. These X-rays, emitted when matter is accelerated to near-light speeds, could reveal details about the dynamics of the accretion disk that are currently hidden from our view. Meanwhile, the Event Horizon Telescope, which famously captured the first image of a black hole's shadow, is already planning upgrades to its global network of radio telescopes. The next generation EHT, or NEHT, will combine data from even more observatories, potentially allowing astronomers to resolve features as small as a few hundred kilometers across the event horizon. This could provide direct evidence of how the black hole's gravity distorts light and how the surrounding material behaves in the extreme conditions near the event horizon. But the story of black holes isn't just about their immediate surroundings. The gravitational waves detected by observatories like LIGO and Virgo have already opened a new window into the universe, revealing the mergers of black holes and neutron stars. These ripples in spacetime carry information about the masses and spins of the objects involved, offering clues about how black holes grow over time. Future space-based gravitational wave detectors, such as the proposed Laser Interferometer Space Antenna, LISA, could detect even more subtle signals, perhaps even the mergers of smaller black holes that contribute to the growth of supermassive black holes. By studying these events, astronomers might uncover how black holes consume their surroundings in bursts of energy, or how they slowly accrete material over millions of years. However, the most exciting possibilities lie in the combination of these different observational techniques. Multi-messenger astronomy, which integrates data from electromagnetic waves, gravitational waves, and even neutrinos, is already reshaping our understanding of cosmic phenomena. For example, the recent detection of a black hole's feeding frenzy, its dramatic outbursts of energy and the subsequent cosmic indigestion might be linked to a cascade of events that involve multiple messengers. If the same black hole emits powerful jets of particles, gravitational waves, or high-energy neutrinos during its feeding, these signals could provide a more complete picture of the process. Future observatories designed to detect neutrinos, such as the IceCube Neutrino Observatory in Antarctica, might catch glimpses of these elusive particles, which can travel vast distances without being absorbed by matter. Such detections could help pinpoint the location of the black hole's activity and reveal details about the environment in which it's feeding. Yet, even with these advancements, there are still mysteries that may challenge our current models. For instance, if the observed cosmic indigestion doesn't align with theoretical predictions about how black holes regulate their accretion, it could force scientists to rethink the mechanisms that govern their behavior. Perhaps the black hole isn't simply consuming its surroundings, it might be interacting with nearby stars, gas clouds, or even other black holes in ways we haven't yet considered. The next generation of telescopes and detectors will need to be equipped to explore these possibilities. Instruments like the Square Kilometre Array, SKA, a next-generation radio telescope array, could provide unprecedented detail on the magnetic fields and plasma environments surrounding black holes. Meanwhile, the James Webb Space Telescope's successor, the Nancy Grace Roman Space Telescope, might offer insights into how black holes influence their host galaxies over cosmic timescales. These missions will not only refine our understanding of individual black holes but also shed light on their role in the evolution of galaxies themselves. As we look to the future, the quest to understand black holes is far from over. Each new observation, whether it confirms existing theories or reveals unexpected phenomena, brings us closer to unraveling the secrets of these cosmic giants. The next chapter in this story will be written by the ingenuity of scientists and engineers who continue to push the boundaries of technology and imagination. And as we await the results of these upcoming missions, one thing remains clear: the universe is still full of surprises, and the study of black holes will remain one of the most thrilling frontiers in modern science. Imagine a black hole, a cosmic vacuum cleaner, devouring nearby gas and dust in a frenzy of gravitational hunger. For years, astronomers have watched these events unfold, capturing the light and energy released as matter spirals into the abyss. But what happens when the feast ends? Recent observations of a distant black hole, located 500 million light-years away, have revealed a dramatic finale, a violent outburst of energy, as if the black hole itself was suffering from cosmic indigestion. This event, studied using telescopes like ALMA and X-ray observatories, offers a rare glimpse into the chaotic life cycle of these monstrous objects. The first takeaway is that black holes don't just consume, they erupt. When the accretion disk of gas and dust around a black hole becomes unstable, it can trigger a sudden release of energy, brighter than entire galaxies. This isn't just a flashy show, it's a critical process that regulates how black holes grow and influence their surroundings. The second revelation is that this outburst wasn't a simple explosion. It was a complex interplay of forces, with magnetic fields and relativistic jets playing key roles in shaping the ejected material. The third takeaway? This event challenges our understanding of black hole behavior. By studying such phenomena, scientists can refine models of how these objects interact with their environments, shedding light on the broader question of how galaxies evolve. But here's the twist: the indigestion observed might not be a one-time event. Some theories suggest that black holes could experience repeated surges as their accretion disks fluctuate, creating a cycle of feeding and expulsion. This raises intriguing questions about the long-term stability of these systems and their role in the universe's cosmic balance. The data from this observation isn't just a snapshot, it's a puzzle piece in a larger picture. By combining radio, optical, and X-ray data, researchers have built a more complete story of what happened. Yet, there are still mysteries. For instance, how exactly does the instability in the accretion disk trigger such a massive outburst? And what does this mean for the surrounding galaxy? These questions drive the field forward, pushing astronomers to refine their tools and theories. As we look to the future, such events will become even more critical. With next-generation observatories, we'll be able to study these cosmic feasts in greater detail, perhaps even spotting similar phenomena in other galaxies. But for now, this black hole story reminds us that the universe is a dynamic place, where even the most powerful objects are bound by the same physical laws that govern our everyday lives. So, what does this mean for us? Well, understanding these processes helps us grasp the forces that shape the cosmos and our place within it. If you've enjoyed this deep dive, consider subscribing to FactVerse for more explorations of the universe's greatest mysteries. And if you have your own theories or questions about black holes, drop them in the comments. After all, science is a conversation, and every observation brings us one step closer to the truth.